Polarity, hydrogen bonds, London, and network. We are going to start off with the term polarity. So what is polarity? Polarity is an uneven distribution of charge, creating slightly positive and negative regions of space on opposite sides of the molecule. And the opposite of polarity is nonpolar. So what nonpolar means is that there's a symmetric distribution of electron charge in a molecule. So by reading the definitions, you can tell that polarity is uneven distribution and nonpolar is symmetric, so like equal distribution from both sides of the regions. So lone pairs on a Lewis dot structure on the central element indicate polarity, that structure is polar except 2, 3 linear and 4, 2 square planar. So these are the two exceptions you need to remember when determining if a structure is polar or nonpolar. Hydrogen bonds. The force of attraction between an H that is bonded to an F, O, or an N on one molecule to the lone pairs of an F, O, or N on another molecule, also known as a superpolar. So we're going to do examples of all of these later in the video, but now we're just going to give the definitions so you can make sense of what each one means and how to identify it. Next is London dispersion. London dispersion is the slight polarity established from the natural movements creating a temporary uneven distribution of charge. And London dispersion occurs in all covalent molecules and single nonmetal atoms like He or Ne. So the last term we're going to talk about before we get to examples is network covalent structures. So network is a nearly endless pattern of covalent bonds in a structure. And this structure is very strong. And to prove that, some examples of network structures are diamond, graphite, and quartz, which, if you know any of those, are very strong structures. Okay, so now we're going to do some examples using the information we know to identify the type of forces present for each structure. So some of them you may need to draw a Lewis dot structure, and some of them you may be able to just tell what it is without needing to draw the structure. So let's go to the first example, Mg, magnesium. So if you look at that on your periodic table, you will need a periodic table out in front of you to look. To help you, you'll see that Mg is metallic, so you will check that off. Okay, the next one is HF. So immediately from our previous notes about hydrogen bonds, we know that a hydrogen bond is when an H is bonded to an F, an O, or an N. So here we can see that H is bonded to an F, so then we can check off hydrogen bonds. But we're not done here. We have to actually draw the Lewis structure to see if it is polar or not. And then the other piece of information we can tell immediately is that it is London dispersion, because anything that is covalent is automatically London dispersion. So, to draw the structure, let's see here. Do H, F, and then the math is 1 plus 7, which is 8. So we're going to add some. Okay, so we're going to add the dots here 2 on each, and then we're going to add 2 more. And we are going to do a double bond on this one. Whoops. Okay. So now we can tell that there are lone pairs, and it is not one of the exceptions. So it is polar indeed. The next example is ICl3. So looking at our periodic table, we'll look for I and Cl, and we can see that they're both nonmetals, so we know automatically that it's covalent. And anything that's covalent is automatically London, so we can check that off. There is no H bonded to an F, an O, or an N, so we don't need to worry about hydrogen bonds. But we do need to draw the Lewis dot structure to see if it is polar or not polar. So we will draw the structure. Cl. And if you do the math, it's 7 plus 3 times 7, which is 28, minus 6, and 22. So you're going to distribute those. Two, 4, 6, 8, 10, 12, 14, 16, 18, and then when you have extras, you add them to the central. So we're going to add 20, 22, and now you can see that the central does have lone pairs, so that means that it is polar. So check that off. Okay, the next example is H2O. So immediately when you see an H in front, you should check to see what it's bonded to. And in this case, it is bonded to an F, an O, or an N. It's bonded to an O. So we know that it is a hydrogen bond. So we can check that off. And since it's covalent, we can immediately check off that is London dispersion as well. So to draw the structure, we'll start off with an O in the middle, bonded to 2 H's, and have 2 lone pairs. And since the central has lone pairs, it is polar. Okay, so the next example is CuO. So you'll look at your periodic table again and find Cu, copper, and oxygen, and let's see. And you'll notice that it's a metal bonding with a nonmetal, and when that happens, you know that it is ionic. So we'll check off the box for ionic. Next we have SeI4, and if you look on your periodic table again, or if you just know, Se and I are both nonmetals, which means it's covalent, and automatically you know that it will be London. And then to find out if it is polar or not, we have to draw the Lewis structure. So we'll go ahead And do that. Okay, and if you do the math, it should be like around 6 plus 4 times 7, which is 34 minus 8 because of the bonds, which leaves you 26. So let's start distributing. We'll start giving each eye 3 pairs. And then we have left 1 pair to give to the SE. So now that we see that the central has a lone pair, we know that the structure is polar. So we can check that off. And there's no H bonded to an F, an O, or an N, so we know it's not hydrogen bonds. The next example is Bi3. So looking at your periodic table, or just knowing B and I, both nonmetals, which makes it covalent and automatically London dispersion. And then to see if it's polar or not, we'll once again draw the Lewis structure. So we have a B, I, and 3 I's. And the math is 3 plus 3 times 7, 24, minus 6 for the bonds, which leaves you with 18 to distribute to 3 I's, which gives you a perfect number, perfect dispersion. So 2, 4, 6, 8, 10, 12, 14, 16, 18, and there's no left over, so you can conclude that it is not polar because there are no lone pairs on the central. So we'll just stick with London dispersion for that one. The final example is diamond, and if you remember from the definitions of some of the structures, the types of forces, you'll remember going over a network, and if you remember network, some examples of network were diamond, quartz, and graphite, and they're the strongest structures. So you can just assume that you will just be checking off network. So this is the end of the video. I hope this helps. Good luck.